Welcome to this comprehensive tutorial on Pytorch scatter and gather operations. These are two fundamental tensor indexing operations that are essential for advanced machine learning implementations. We'll explore torch.scatter, which writes values to specific indices in a tensor, and torch.gather, which reads values from specific indices. These operations are inverse to each other, and they're crucial for things like implementing attention mechanisms, creating one-hot encodings, working with sparse data, and batch processing with non-uniform indices. Let's dive in and understand these powerful operations step by step. Let's start by importing the necessary libraries. We're bringing in Pytorch as our main framework, along with NumPy for array operations, Matplotlib for visualization, and Seaborn for making our plots look nicer. We'll also set a random seed to ensure our results are reproducible throughout this tutorial. Before we dive into the operations, let's understand the dimension parameter. This is crucial because it specifies which dimension the index tensor applies to. When dim equals 0, the index applies to rows or the first dimension. When dim equals 1, it applies to columns or the second dimension. And when dim equals 2, it applies to depth or the third dimension. This concept will be fundamental throughout our tutorial. Now let's look at the basic scatter operations. The scatter formula might seem complex at first, but it follows a pattern. For a 3D tensor, when dim equals 0, we have self at index ijk, j, k equals source at ijk. When dim equals 1, we have self at I, index ijk, k equals source at ijk, and when dim equals 2, we have self at ij, index ijk equals source at ij. Don't worry if this seems abstract. We'll see concrete examples that make it clear. Let's start with the simplest possible example, a one-dimensional scatter operation. Here's our simplest scatter example. We create a source tensor with values 10, 20, and 30. Our index tensor tells us where each value should go, with positions 2, 0, and 1. We start with a target tensor of all zeros. After the scatter operation, source value 10 goes to position 2, 20 goes to position 0, and 30 goes to position 1. Let me run this to show you the result. Perfect! As we can see, our source values 10, 20, 30 got rearranged according to the index positions. The result is 20, 30, 10. Notice how source at position 0, which is 10, went to index position 2. Source at position 1, which is 20, went to index position 0. And source at position 2, which is 30, went to index position 1. This is the fundamental behavior of scatter. It writes values to the positions specified by the index tensor. Now let's move on to two-dimensional tensor operations, which are more common in practice. Let's explore two-dimensional scatter with dim equals 0, which operates on the row dimension. In this example, we're working with a 2 by 3 source tensor containing values 1 through 6. Our index tensor specifies which row each value should go to. With dim equals 0, each value from source at position I, j goes to row index ij, but stays in the same column j. For example, source at position 0, 0, which is 1, goes to result at row 0, column 0, because index at 0, 0 is 0. Great, look at the result tensor. We can see that value 1 ended up at position 0, 0, value 5 is at position 1, 1, and value 3 is at position 2, 2. The key insight here is that with dim equals 0, we're controlling which row each value goes to, but the column position stays the same. This is why source at 0, 0 equals 1 goes to result at 0, 0. The row is determined by the index value of 0, but it stays in column 0. Now let's look at two-dimensional scatter with dim equals 1, which operates on the column dimension. Here we have the same source tensor, but now with dim equals 1, we're controlling which column each value goes to while keeping the row fixed. Each value from source at position I, j goes to row I, but moves to column index ij. For instance, source at 0, 0, which is 1, goes to result at row 0, column 2, because index at 0, 0 is 2. Excellent, notice how the pattern is different from dim equals 0. Now value 1 is at position 0, 2, value 2 is at 0, 0, and value 3 is at 0, 1. The values stay in their original rows but move to different columns based on the index tensor. This demonstrates how the dim parameter fundamentally changes the behavior of the scatter operation. let me create a visualization function to help us see these two-dimensional scatter operations more clearly. We'll use heat maps to show the source tensor, index tensor, and resulting tensor side by side. Here we can see two beautiful visualizations. The first shows scatter with dim equals 0 where values move between rows. The second shows scatter with dim equals 1 where values move between columns. The color coding helps us track how values flow from the source tensor through the index mapping to produce the final result. These visualizations really help clarify the difference between operating on different dimensions. Now let's explore gather operations, which are the inverse of scatter. The gather formula reads values from specific positions rather than writing to them. For a 3D tensor with dim equals 0, output at ijk equals input at index ijk, jk with dim equals 1, output at ijk equals input at I, index ijk, k, and with dim equals 2, output at ijk equals input at I, j, index ijk. Let's see two-dimensional gather with dim equals 0. In this gather operation with dim equals 0, we're reading from different rows while keeping the column fixed. The result at position I, j equals the input at row index ij, column j, so result at 0, 0 reads from input at row 0, column 0, which gives us 1. Result at 0, 1 reads from input at row 1, column 1, which gives us 5. Perfect. The result shows we've successfully gathered values 1, 5, 3 in the first row and 4, 2, 6 in the second row. This demonstrates how gather reads from the input tensor based on the index values. With dim equals 0, we're selecting which row to read from while keeping the column position fixed. Now let's look at two-dimensional gather with dim equals 1. With dim equals 1, we're reading from different columns while keeping the row fixed. Result at position I, j equals input at row I, column index ij for example. Result at 0, 0 reads from input at row 0, column 2, which is 3. Result at 0, 1 reads from input at row 0, column 0, which is 1. Excellent. The result shows 3, 1, 2 in the first row and 5, 6, 4 in the second row. Notice how we're staying within each row but selecting different columns based on the index values. This is the key difference from dim equals 0. We're controlling column selection rather than row selection. Now let's tackle three-dimensional tensor operations, which add another level of complexity but follow the same principles. Let's explore three-dimensional scatter with dim equals 0, which operates on the batch dimension. For three-dimensional tensors, we have an additional dimension to work with. Here we create a 2 by 2 by 2 source tensor with values 1 through 8. With dim equals 0, each value from source at position I, j, k goes to batch index ijk, but stays at the same position j, k within that batch. This is like moving values between different batches while preserving their spatial position. Great! Looking at the result, we can see how values have been redistributed across the two batches. Value 1 stayed at batch 0 position 0, 0, but value 2 moved to batch 1 position 0, 1. The key insight is that dim equals 0 controls which batch each value goes to, while the spatial positions within each batch are preserved. Now let's see three-dimensional scatter with dim equals 1, operating on the height dimension. With dim equals 1 on a three-dimensional tensor, we're controlling the height or row position within each batch. Source at I, j, k goes to batch I, row index ijk, column k the batch and column positions are preserved, but we can move values between different rows within each batch. Perfect. The result shows how values move between rows within their respective batches. In batch 0, value 1 stays at position 0, 0, but value 2 moves to position 1, 1. This demonstrates how dim equals 1 gives us control over the vertical positioning while keeping batch and horizontal positions fixed. Let's complete our three-dimensional exploration with dim equals 2, operating on the width dimension. With dim equals 2, we're controlling the width or column position. Source at I, j, k goes to batch I, row j, column index, ijk. This time the batch and row positions stay the same, but we can move values between different columns. Excellent. Notice how in batch 0, value 1 moved to position 0, 1, and value 2 moved to position 0, 0. They swapped their column positions. This shows how dim equals 2 gives us control over horizontal positioning while preserving batch and vertical positions. Now let's demonstrate gather operations for all 3 dimensions of a 3-dimensional tensor. Here we're demonstrating gather operations on all 3 dimensions of our 3-dimensional tensor. With dim equals 0, we select which batch to read from. With dim equals 1, we select which row to read from within each batch. And with dim equals 2, we select which column to read from. Each dimension gives us different control over where we're reading values from. All 3-dimensional gather operations have been verified successfully. This confirms that gather works consistently across all dimensions, always reading from the positions specified by the index tensor while keeping other dimensions fixed. Now let's explore a fundamental property. Scatter and gather are inverse operations. This means if we scatter values and then gather them back using the same indices, we should recover the original tensor. Let's demonstrate this inverse relationship. We start with an original tensor containing values 1 through 9. We scatter these values using our index tensor, which rearranges them. Then, we gather from the scattered result using the same index tensor, and we should get back our original values. Perfect. As you can see, after scattering the values to new positions and then gathering them back with the same indices, we've recovered our original tensor exactly. This proves that scatter and gather are true inverse operations. This property is very useful in practice when you need to temporarily rearrange data and then restore it to its original structure. Let me visualize this inverse relationship to make it even clearer. We'll show the original tensor, apply scatter, then apply gather, and see how we get back to where we started. This visualization beautifully shows the complete cycle. Starting with our original tensor on the left, we apply scatter with our index tensor to get the rearranged middle result. Then applying gather with the same index tensor brings us back to our original values on the right. The color patterns help us track how values move through the transformations and ultimately return to their starting positions. Now let's explore some advanced features. Pytorch's scatter operation supports reduce operations, which are incredibly useful when you have duplicate indices. Here we're using scatter with reduce equals sum for accumulation. Notice that our index tensor has duplicates. Position 0 appears multiple times. With regular scatter, only the last value would be kept. But with scatter underscore reduce and reduce equals sum, all values targeting the same position get added together. The initial value of 1 plus 2 additions gives us 3 at position 0, 0. Excellent, look at the result. Position 0, 0 has value 3, which is the initial 1 plus 1 plus 1. Position 1, 1 also has 3 for the same reason. This accumulation behavior is essential when you need to aggregate values that map to the same position, like in histogram creation or weighted averaging. We can also use scatter underscore reduce with multiplication. Here we start with a target tensor of all 3s and source values of all 2s. When multiple source values target the same position, they get multiplied together along with the initial value. Perfect. Position 0, 0 shows 12, which is 3 times 2 times 2. This demonstrates the product reduction. Reduce operations make scatter much more powerful for aggregation tasks where you need to combine multiple values mapping to the same location. Let's explore how scatter and gather work with sparse tensors and gradients, which is important for memory-efficient deep learning. Here we're comparing dense and sparse gradients with the gather operation. When we use gather normally, Pytorch creates a dense gradient tensor with mostly zeros. But when we specify sparse underscore grad equals true, Pytorch creates a sparse tensor that only stores the non-zero gradient values. This can save significant memory when working with large tensors where only a few positions have gradients. Great, we can see that the dense gradient has 9 non-zero elements out of 25 total positions. The sparse gradient stores exactly the same information, but only keeps track of those 9 non-zero values and their positions. This sparse representation can be much more memory efficient for large-scale operations. Let's work directly with sparse tensors to see how they interact with scatter and gather operations. We're creating a sparse tensor in coordinate format, or COO format. We specify the indices where non-zero values exist and the values at those positions. The sparse tensor efficiently represents a mostly empty matrix by only storing the 4 non-zero values instead of all 9 positions. Perfect. The sparse tensor operations are verified. We can see the sparse representation with just 4 values at specific coordinates, and when we convert it to dense format, we get the full 3 by 3 matrix with zeros filled in. Gather operations work on the dense version, maintaining compatibility with standard Pytorch operations. Now let's look at practical applications of scatter and gather in real machine learning scenarios. First application is creating one-hot encodings, which is fundamental for classification tasks. Here we're creating one-hot encodings using scatter. We have class labels 0, 2, 1, 3, 1 for 5 samples and 4 classes. By scattering ones at the positions indicated by the labels, we create a one-hot matrix where each row has exactly one value of 1 at the position corresponding to the class label. Perfect. The one-hot encoding is created successfully. Each row has exactly one value of 1.0 at the position corresponding to its class label. Sample 0 has class 0, so position 0 is 1. Sample 1 has class 2, so position 2 is 1. This is much more efficient than manually creating these encodings and is differentiable for use in neural networks. Second application is batch index selection, useful for selecting specific elements from sequences. This function selects specific time steps from sequence data for each batch element. Imagine you have sequences of length 10 and you want to extract time steps 0, 5, and 9 from the first batch, time steps 1, 3, and 7 from the second batch, and so on. Gather makes this complex indexing operation simple and efficient. Excellent, we've successfully selected specific time steps from each batch. The input had shape 3 by 10 by 4, representing 3 batches of 10 time step sequences with 4 features each. After selection, we have shape 3 by 3 by 4 with 3 selected time steps per batch. This pattern is common in attention mechanisms and sequence modeling. Third application is embedding lookup, which is the foundation of word embeddings in NLP. Here we're implementing embedding lookup manually using gather. We have an embedding table with 100 words and 16 dimensions per word. Given token indices, we use gather to fetch the corresponding embedding vectors. This is exactly how Pytorch's embedding layer works internally, demonstrating that gather is the core operation behind word embeddings. Perfect. Our manual embedding lookup using gather produces exactly the same results as Pytorch's built-in embedding layer. This shows that gather is the fundamental operation underlying embedding lookups in neural networks. Understanding this helps you appreciate how transformer models and other NLP architectures efficiently retrieve word representations. Let's analyze the performance characteristics of scatter versus gather operations. Now I'm running a performance benchmark comparing scatter and gather operations across different tensor sizes. We'll test with 100 by 100, 500 by 500, 1000 by 1000, and 2000 by 2000 tensors to see how performance scales. The benchmark results show interesting performance characteristics. For smaller tensors, scatter and gather have similar performance. As tensor size increases, we can see how the execution time grows. The visualization clearly shows that both operations scale well with tensor size, though the exact performance can vary based on hardware and memory patterns. In practice, gather tends to be slightly faster since it's a read operation, while scatter involves writing, which can have more complex memory access patterns. Now let's discuss common pitfalls and best practices when using scatter and gather. First pitfall is index out-of-bounds errors. Here we're demonstrating index bounds checking. Valid indices for a size 3 tensor are 0, 1, and 2. If we try to use index 3, we'll get an error because it's out of bounds. The best practice is to always validate your indices before using scatter or gather operations. I've included a safe_scatter function that checks bounds before performing the operation. Good, we can see that valid indices work fine, but invalid indices cause errors. The key takeaway is to always validate that your index values are within the valid range of 0 to size -1 for the dimension you're operating on. This prevents runtime errors and makes your code more robust. Second pitfall is dealing with duplicate indices in scatter operations. This demonstrates what happens with duplicate indices in scatter. When multiple source values target the same position, only the last one is kept with regular scatter. This can lead to unexpected results. The solution is to use scatter_reduce with an appropriate reduction operation like sum or multiply when you need to handle duplicates properly. See the warning? With regular scatter and duplicate indices, we lost data because only the last values were kept. But scatter_reduce with sum correctly accumulated all values. This is crucial to understand when working with operations that might produce duplicate indices, like pooling or aggregation operations. Let's wrap up with a comprehensive summary of everything we've learned. Scatter and gather are fundamental Pytorch operations for advanced indexing. Scatter writes values to specified indices, making it destination-based. Gather reads values from specified indices, making it source-based. They are inverse operations. The dimension parameter controls which dimension the index applies to, with other dimensions preserved. Index tensors must have the same number of dimensions as input and output. Values must be within valid range, and the shape determines output shape for gather. Best practices include always validating index bounds, using scatter_reduce for accumulation, considering sparse gradients for large-scale operations, and profiling performance for your specific use case. Common applications include one-hot encoding, embedding lookups, attention mechanisms, batch index selection, and sparse tensor operations. Here's your quick reference cheat sheet for scatter and gather operations. For scatter with dim equals 0, target at index ij, j equals source ij with dim equals 1. Target at index ij equals source ij for gather with dim equals 0. Output ij equals input at index ij, j with dim equals 1. Output ij equals input at index ij. Remember that scatter modifies existing tensors and supports in-place operations, while gather creates new tensors with no in-place version. Scatter can use reduce operations for handling duplicates, and gather supports sparse gradients for memory efficiency. And that completes our comprehensive tutorial on Pytorch scatter and gather operations. We've covered everything from basic concepts to advanced applications, performance considerations, and best practices. These operations are powerful tools in your Pytorch toolkit, enabling efficient tensor manipulation for complex machine learning tasks. Keep this tutorial as a reference, and happy coding!